Hi, 555 as a Schmitt trigger. It's a fairly simple configuration, and let's look at the circuit. This is a symbol of a Schmitt trigger. You have an input and an output. That Schmitt trigger is an inverting Schmitt trigger, which is same as what we have here with the 555. So if we connect pin number 6 and 2 together, that will be our input, and the pin number 3 will be our output, and it will behave just like a inverting Schmitt trigger. Let's see how it works. This is the internal configuration of the 555. So in our Schmitt trigger configuration, we have pin number 6 and 2 connected together, and that's our output. So let's see, we are feeding in a voltage which is increasing. So at the very start, your voltage is almost 0, and we discussed last time these voltages at this node is VCC divided by 3, and this node will be VCC 2 times VCC divided by 3. If you want to refresh the memory, you can watch the first video. I'll put the link below. So when it's 0 volt, this comparator will be on, and that would set the flip-flop, and that would output high output. So as the voltage increases, it would go beyond VCC divided by 3, but nothing would happen. Even though this set pin goes to low, the flip-flop wouldn't change, output remains high. And as it increases, the next threshold is the 2 times VCC divided by 3. So what happened when it increased that threshold? So this comparator will be activated and it will reset the flip-flop. So that will give us a low output. So if the voltage increases and if it comes down, let's see what happens. So if the voltage drops below 2 times VCC divided by 3, this output would go low, but the output of the flip-flop wouldn't change, so it will remain low until the voltage goes below VCC by 3, and that's when this flip-flop activate and set the flip-flop, this comparator activate and set the flip-flop, and the output will go back to high. As you can see, let's plot that behavior in a graph. So our input is almost at the 0 now, so it is increasing but still below VCC divided by 3. So when it's VCC divided by 3, our output is at high level, and when it goes below VCC divided by 3, nothing will happen. The output is still high until the input voltage go beyond 2 times VCC divided by 3, and that's when the output goes to low, and it will remain low for any input that is greater than 2 times VCC divided by 3. So when we decrease the voltage, so we're decreasing, but nothing will happen when the voltage goes below 2 times VCC divided by 3. It will remain low until it goes below VCC divided by 3, and that's when our output goes high. So that's our hysteresis voltage for this Schmitt trigger made out of a 555 timer. How good is that? Let's compare that to a commercial Schmitt trigger which I recently used in one of my designs. So that's the Schmitt trigger I used. It's a fairly small package, and it's a NAND gate, not a NOT gate like we saw in our 555, but it's the inputs have the similar characteristic. So if you look at on the input voltage thresholds, as you can see, it has two voltage thresholds. So that's VT plus and VT minus. So they are the positive threshold and the negative threshold. They are just like the two voltage thresholds that we saw with our 555, and it also change with the input voltage. So there are values given for different supply, and the input the threshold voltage differ based on the supply as well, just like our 555. But there is a good news with our 555. With this commercial Schmitt trigger, you can't change these values. They are fixed for a given supply voltage. But with the 555, you can fiddle with those voltages. Let's see how we do that. Remember pin number 5? We talked about in my last video. I'll put that link down below as well. See where it's connected. It's connected to this node. What happens if we connect a resistor into VCC? So that makes two parallel resistors here, and that will increase the voltage between these two resistors. So these values will not be 2 times VCC divided by 3 or VCC divided by 3. They will be increased than what it was before. Similarly, we can connect the same resistor or similar resistor to the ground and see what happens then. So that will be that resistor, and these two resistors will be parallel. So the voltage between this resistor network will be less than 2 times VCC divided by 3, and hence this voltage will be half of that, but it will be definitely less than the previous voltage thresholds. That's enough talking. Let's go to the breadboard and see how they work. Okay, this is the setup. I've got my input. I'm feeding a 1 kHz triangular signal, peak to peak 5 volt, offset 2.5, so it doesn't go below 0. So that's my input, and the output is connected to the oscilloscope. Alright, I have set the two cursors from channel 1, which is our input, to the two threshold voltage. So we got E, which is 1.6, that is close to 5 divided by 3 because my supply is 5 volts, and the second threshold is S, so that's 3.44, that's 2 times that, we're roughly there. And see what happens when the voltage go below that E voltage. That's when our output goes high, and it will remain high until our voltage go above the S voltage, and that's when the output goes low. So that's our Schmitt trigger working perfectly. And let's see whether we can change the threshold voltage by connecting a resistor to pin number 5. Okay, I got a 1K resistor connected to pin number 5, but the other end of the 5K has not connected to anywhere yet. Let's see, first we connected to the positive rail. So our 2 voltage has to be more than what we got at the moment. Let's see what happened. There. If we look closer, that was the previous voltage. Now it has gone higher, and the same with the higher threshold as well. That's where it was before. Now that's where it is now. Those 2 voltages has gone higher. Let's see if we connect that to the negative rail. They should go lower. There you go. That's the new VCC divided by 3, the new low threshold. And new high threshold is just about there. They got really narrow. The threshold, the Schmitt trigger voltage, no, the hysteresis voltage got really low in this case, and the hysteresis voltage would go higher than normal if we connect this to the positive rail. So again, depending on the resistor you connect to the pin number 5 and between the positive or the negative rail, you can change the hysteresis voltage and the 2 threshold voltages as well. Let's see a practical example. This is my practical example where I'm using a 555 time IC as a Schmitt trigger. What I'm trying to do here is to measure the system frequency, the frequency of the electricity that comes to my house. So don't worry about the frequency, it's not 100% accurate. I will discuss more about the circuit now. So in a nutshell, this is my circuit. I got my supply here and a transformer to step down to a manageable voltage, and I got a voltage divider to even further manage to reduce to a manageable voltage for 0 to 5 for the 555. So I got the supply as 5 volt. So our 555 is configured in our Schmitt trigger configuration, and that drives the Arduino. I got a digital input, doesn't matter, any digital input is fine, and the Arduino is driving the LCD.
The code is fairly simple. We need to include the liquid crystal header for the LCD, and then we declare a LCD display, and this is our digital input pin 6. That's where the pulse input is coming in from. That's from our 555, and some local variables. Setup is fairly straightforward. Again, we need to set the pulse input pin as an input, so that's all good. In our loop we have this 2 pulse ln function which measure the pulse length in microseconds. So from the input pin we measure the high pulse length, and again we measure the low pulse length. So the addition of those two will be the period of the signal coming in, and the frequency is 1 million divided by period, because its period is coming in microseconds. The rest is just displaying results on the LCD. We wait for 1 second before we do that all over again. So this is a fairly simple frequency measurement program. It doesn't do any averaging or anything like that. Just wait for a second and do another sample and display. So there is a lot we can improve in this program, but this is good enough for us. Our focus is using the 555.
So the job of the 555 is, again as I said, is to convert the analog signal into a digital one. So after our rectifier we have a signal like this, a half wave rectified signal, further voltage reduced, but at the pin number 3 I get a digital output because the Schmitt trigger, we have 2 comparators in there, will convert our analog into a digital signal. But what one would say, why can't we use a comparator, a simple comparator, to get this done? Well, theoretically, absolutely, why not? So, if you use a jelly bean comparator, I can use LM311 for that. So you can set one voltage here, one of the 2 inputs. Say we have inverting input there, we have a set voltage, and to the non-inverting input we have our analog signal fed in. So when the analog signal voltage is more than our threshold voltage here, it will produce a high output, and when it is less, it will produce a low output. But let's see what's the problem in that. Okay, so this is the 2 methods we just discussed. So channel 1, the yellow trace, is the output of the 555, which is a Schmitt trigger. And the blue trace is the output of the LM311 comparator. The waveforms are slightly different, but the important is what we are trying to measure is the frequency. Frequency is pretty steady by the look of it. But let's go deeper and see what the problem is with the comparator method. So I'm going to zoom in a little bit. So I'm zooming in on the 555, the rise. The rise is very clean. There's a bit of overshoot, but that's fine. There's no oscillation there. So let's see on the fall. Let's set the trigger to the falling edge. Let's zoom in. Falling edge again, fairly clean. Now let's say the same from the LM311. We'll set the trigger to channel 2, and now let's see rising edge. Oh, look what we got here. Got a fair bit of oscillation happening. Let's see what's happening in the falling edge. The oscilloscope having trouble keeping it steady, but yeah, there you go. It's the same oscillation, just like we saw at the rising edge. So there's a bit of oscillation happening at the rising and falling edges. Why? Because of noise. The signals are not ideal. There's noise in it, and this tiny little variation is enough for the comparator to oscillate when the voltage is very close to the threshold voltage. And that's why we should always use a Schmitt trigger for applications like this. But when it's like this, by the look of it, everything looks good. Now let's see what happened if we use the comparator output as the input to the Arduino and see what the frequency measurement would do. So at the moment things are fairly steady. I got a close to 50 Hertz. So that's my input. D6 is the frequency input. Let's take that out. So now the Arduino having trouble reading the frequency at all. There's nothing there. Let's feed the comparator output to the Arduino. And let's reset as well. Ooh, look at that. Let's reset again. Frequency is all over the place. It's not steady at all. So those little oscillations that we saw at the rising and falling edges, it's really confusing the Arduino, and it's having hard time figuring out the frequency. Let's switch back to the 555 output and reset this. There you go. Fairly steady frequency measurement. So if you like this video, give us a thumbs up and don't forget to share and subscribe. Thank you for watching, and I'll see you next time.